All right, everyone, welcome to the broadcast. We will be starting very shortly. Sit tight as we allow folks to join and get ready for a very exciting and interesting conversation. All righty. Hey, everyone, and welcome to the broadcast. I'm Sam Charrington, host of the TWIML AI podcast. I am super excited to be joined by an amazing panel to take on the topic of model explainability. As the use of machine learning in critical environments like government and jurisprudence, business, and other settings has exploded over the past few years, the requirement to understand the decisions that machine learning models are making has exploded as well. This is accentuated by the increasing popularity of opaque models like deep learning. And all of this has set the stage for a really thriving field of model explainability in both research and practice. And in this panel discussion, we're excited once again to bring together experts, researchers, and practitioners to share their unique perspectives and contributions in this field. So thanks so much for joining us. We'll be exploring a bunch of really interesting topics. But before I introduce our panelists, I want to send a huge thanks to our friends at IBM for supporting this discussion. IBM is committed to educating and supporting data scientists and bringing them together to explore technical, societal, and career challenges through the IBM Data Science Community site, which has over 13,000 members. They provide a place for data scientists to connect, collaborate, and empower one another. IBM's data science community is a great place to engage with other practitioners and access information and resources that inspire creativity and innovation. Go to twimlai.com/IBM community to join. And when you're there and when you join, you get a free month of select IBM programs on Coursera. So at this point, I would like to introduce our panel. You may recognize some of them from previous podcast interviews. And if you are following along on YouTube, we will be dropping links to those in the chat. But please join me in welcoming them. First up is Raed Ghani. Raed is a professor in the machine learning department in the School of Computer Science and the Heinz College of Information Systems and Public Policy at Carnegie Mellon University. Raed, thanks so much for joining us. Great. I think we fought over the mute button, Raed.
Okay. Are you introducing everyone, or?
I am introducing everyone. I just wanted to say hi to you. Next up is Solon Barocas. Solon is an assistant professor in the Department of Information Science at Cornell University, as well as a principal researcher in the New York City lab of Microsoft Research. And he'll be speaking on hidden assumptions behind counterfactual explanations. I think I missed Raed's topic, which is explainability use cases in public policy and beyond. Next up is Kush Varney. Kush Varshney. Kush is a distinguished research staff member and manager at IBM's TJ Watson Research Center focused on artificial intelligence. And Kush will be speaking on model explainability as a communications challenge. Next up, we've got Alyssa Labjanova. Alyssa is the CTO of a stealth startup and former CTO in residence at the Allen Institute for Artificial Intelligence, and she'll be speaking on stakeholder-driven explainability. And last but certainly not least is Hema Lakaraju. Hema is an assistant professor at Harvard University with appointments in the business school and the Department of Computer Science. And she'll be speaking on adversarial attacks, misleading explanations, and solutions. So a quick note about our format today. Each panelist will be presenting for about 5 to 8 minutes on their topic. Following these presentations, we'll be opening up the floor for discussion and audience questions. And it's really my sincere hope for this session, as with all of our discussion events, that you, the audience, drive a good part of our discussion today. We should have about 40 minutes for the audience-driven segment of today's event. So please be sure to note your questions in the YouTube chat so that I can relay them to our panelists. Finally, we are looking forward to bringing you more discussions like this on a wide range of topics. To be notified when we schedule future discussions, subscribe to our newsletter at twimlai.com/newsletter. So let's get started. We'll be kicking things off with Raid Ghani.
Thank you, Sam. And thanks to all of you who are here. Hopefully this will be an interesting and discussion. So I'm going to sort of quickly frame some of my thoughts and then leave a lot more time for the more interesting conversations. As Sam mentioned, I'm at Carnegie Mellon in the Public Policy College and Computer Science Machine Learning Department. And a lot of the work that has been focused on the last several years is really looking at how do we build, pick your favorite buzzword, machine learning, AI, whatever is trendy and IBM wants to sell today, and human collaborative systems, right? How do we build systems that work together with humans and machines to solve social and policy problems that end up with fair and equitable outcomes for people? So that's kind of the framing of a lot of the projects that I work on in healthcare and education, criminal justice, policing, economic development, workforce. And over the last many years of working on this, what keeps coming up is this issue of explainability across different types of problems, across different types of users. And if you sort of, a lot of the research that's been done, we think of sort of explainability as this monolith concept where we're trying to explain what some ML AI model is doing. In reality, in actual, you're trying to solve a specific problem, you've got a lot of different use cases. Like there's a whole, taxonomy of use cases that comes up, especially in sort of public policy problems, right? So most public policy problems are luckily not automated, but they're also not just humans because, humans are not the greatest decision makers, neither are machines. So most public policy problems, you're sort of working interactively, collaboratively. And so what we've been doing over the last few years is looking at, the specific use cases that show up and developing a taxonomy that consists of what the use case is, for each use case for explainability, what the users are, who the users are, and based on that, what these methods need to do. And the idea behind that is that we can use this taxonomy to evaluate the applicability of existing methods. So when a new method comes up, and we can kind of figure out, does it even apply to these types of problems? And if it doesn't, what are the gaps that we need to focus on to kind of give the structure to this type of work? So I'll kind of give you some of these use cases, and there are kind of 5 big use cases that involve different types of users and goals for each of them. So the first one really is people who build machine learning, AI, data science systems, right? People like us who are building them. The use case there is really debugging, where I'm building a system and before I even show it to somebody else, I want to sanity check I want to debug. And a really common example of detecting leakage, right? We build a model and we look at some sort of explainability thing and we see, there's a feature that's really important. And it turns out it's a proxy for the outcome variable that we're, and we're not going to show this model to somebody because it would be really embarrassing. We've all been there. But if we didn't have, so that's like a very simple use case where we want to debug the model that we're building, and we have to kind of deal with that. A second use case is we actually need to instill trust and credibility to the people who are making decisions with the model. We need to kind of make sure they trust it in order for them to use it. And there, the users are the policymakers often, or the people who are managing teams who are going to use this. So they need to trust it. And in order for them to trust it, it needs to sort of give them comfort and some sort of a understanding of what it's doing and why it's doing it. It doesn't need to do things around individual explainability and local explainability. It's kind of more of a macro. And if they don't trust, the reason we want to make sure we do that is they don't trust the system, they're not going to use the system. If they're not going to use the system, who cares how accurate it is? It's not going to have any impact. So it's a waste of time building one that doesn't get used, right? The third use case is, in order to improve the performance of the system, we need explainability. And let me sort of describe what that means, right? A lot of these systems, so for example, one of the systems we were building a couple of years back was working with the health department and working with a hospital system to identify which HIV positive patients are not going to come back for their next appointment. If they don't come back and get their prescription, they become likely to spread, and that's a problem. And so in this case, there's a person in the middle who is getting a recommendation saying this person is unlikely to come back. Now, in a lot of these real problems, the computer is mostly wrong. It's better than a human, it's better than random, but it's still 30-40%, let's say, correct. And so in that case, we want the person who's taking this recommendation to sometimes override the system and sometimes agree with the system. And ideally, then explanation can help them figure out, ooh, this explanation sounds a little fishy. I think you're picking, if it says, this person is unlikely to come back because they were born on a Monday, I don't really buy that. That might be accurate to what the model thinks, but the model is probably wrong in this case. So if I can use this type of hints to override the model, then the performance of the overall system increases. And that's a different use case than the other two. The fourth use case is very similar, the same user, but different goals. So the first use case is I'm predicting if somebody is going to come back to the doctor or not, but my goal is not the prediction. My goal is to assign them one of many interventions. Are they not going to come back because of transportation issues? Are they not going to come back because of they forget, or because they don't think it's helping them, or because they're just tired of coming back? Each of those reasons for not coming back has a different intervention. And we need to help this person in the middle figure out which intervention is going to be most effective. And an explanation is a really good way of doing that. But the method you need to develop for that explanation is very different than the one for debugging, because it's a different type of user, and for trust, because we're not just asking them to trust the system, we're asking them to assign an intervention. A fifth use case is recourse, and that's been one that's been studied quite a bit, where I'm not trying to help somebody make a decision. I'm telling you, you were denied a loan because of A, B, and C, and if you could only change B, if you can increase your income, then we will be able to give you the loan. And that's the user there is the person who's being affected by the ML decision, and we need to develop something that can, that's actually that can help with the recourse. There are other users as well. These are the big ones. The other ones, for example, looking at bias and fairness, can an explanation help us better understand what's going on so we can be more confident about fairness things? We can figure out another couple of things around how useful is a particular data source. But the idea sort of behind these 5 use cases is that each of these use cases has different set of users, different goals, and that means different methods for explainability need to be developed for each of those use cases. The problem is today, a lot of the work is either very generic, where the people are looking at sort of very, it's not tested on mostly real data. It's sort of standardized, some standard data set. It's not really tested on real problems. It's made up problems. It's not tested on real people. It's mostly mechanical Turkers who are kind of real, but they're not a proxy for social workers, physicians, anybody sort of doing real things. And then they're not tested on real metrics. They're tested on some useless metric like AUC, which nobody cares about in the real world. I'm being provocative on purpose, just to poke people who are going to then complain. And hopefully, the idea behind doing this is that what we're trying to do is set up this taxonomy so that people who are working in this area, they start with a real problem. If they have a real problem, a real use case, figure out which goal you're trying to achieve and build explanation methods for that goal. Or if you're starting from a method, identify which use case does it fit into, and then partner with people who have that type of a problem, work with people, problems, and data that match that, and then sort of hopefully set up a test bed where we can collaboratively work on these types of problems. Because these require real partnerships. These require access to real problems, real people, and real data. And it's not a give me some data and I'll work on it. It requires access to people interactively. And so I think what we need to do here is to sort of build a collaborative setup where people interested in these areas have access to these things. And in return, they have to build something that is useful for the organizations that are helping them. So yeah, so that's kind of my quick overview, and looking forward to hearing from the other people and then having a good discussion.
Awesome. Raid, there is a bunch of interest in learning more about your use case taxonomy. Is there a quick paper or link that we are
actually writing something up right now, so maybe it's almost done. So we'll post that in the probably next couple of weeks.
Okay. So Raid will keep us posted, and we will do our best to keep you posted. Following this event, we will be posting up a notes page with a bunch of resources, and we'll send you an update as to where to find that, and just keep an eye on that. All right. Next up is Solon Barocas. Solon?
Thanks, Sam. I'm really pleased to be able to follow on from Raid's excellent taxonomy. What I'll talk about today, I think most closely relates to what Raid characterized as this recourse type of explanation. And I'll present some ideas from joint work that I've done with Andrew Selps, who's a professor in the law school at UCLA, and Manish Raghavan, who's a CS PhD student at Cornell. So in particular, we looked at this kind of increasingly popular style of explanations known as counterfactual explanations. And for those who are unfamiliar, this is explaining a decision by sort of saying, along the lines of what Raid described, what would have to have been different for you to have achieved a different outcome. So if only you had made, $2,000 more, maybe you would have been able to obtain this loan style, an explanation of that style. And although this is a sort of recent wave of work within computer science, this style of explanation has a much longer history actually in credit, where at least in the United States, there are a set of laws that require that when people are subject to an adverse decision, like a loan rejection, that creditors actually need to give explanation for why that person was denied the loan. And these explanations take the style of offering so-called principal reasons, so specific reasons for the denial. And that might be not specifically that you should have made more money, but perhaps that your income was too low, or maybe that you weren't at your job long enough, or things of this sort. This particular style of explanation has become very popular for a number of reasons. So first of all, it sort of seems to sidestep what had, at least for a couple of years, seemed like a potential catastrophe for machine learning, where legal requirements for explanations were potentially seen as hard constraints on model complexity. And if model complexity is one of the sources of model performance, there seems to be a kind of strong tension between the requirement to explain and the possibility of developing highly accurate models. And with this style of explanation, there is no constraint on model complexity because the model itself can be arbitrarily complex. All that really matters is that you be able to provide these specific kinds of explanations. Similarly, there's a sense in which these styles of explanations can help protect intellectual property and limit gaming because there's no disclosure of the underlying model. And so instead, these sort of piecemeal small explanations of a particular decision, not the model overall. It could also provide what feels like a justification for an adverse decision, or in the case of counterfactual explanations, concrete instructions for what you would have to do to achieve a different outcome. So not just an explanation, but an explanation that gives you instructions for trying to change your chances of succeeding in the future. And finally, it can automate the process of generating these explanations. So rather than being something that someone has to work out manually, there's now an automatic procedure that people using machine learning models can employ to produce these explanations, and in some cases, comply with the law. And so in this paper, we try to point out that while this is a very attractive proposition, and there are good reasons to actually consider this, given these desirable properties, that there are a number of challenges here that actually make it difficult to work in practice, and that we really need to think carefully about these challenges before we adopt this style of explanation with the expectation that it will serve the kinds of goals I just mentioned. So I'll just talk a little bit about those assumptions and maybe touch on the end some ways the law thinks about this as well. OK, so the most basic point is that these counterfactual explanations or principal reason explanations are essentially saying that if some feature value had been different, then you would have received a different outcome. And what's important to recognize here is that there's infinite number of ways to possibly generate explanations of that sort. There's no right answer, right? You can give many possible explanations of that type, which just happen to highlight a different feature that would need to change. And so there's a lot of latitude on the part of the decision maker when it comes to which features to actually highlight and which ones to kind of instruct people to change. And here, the thinking is that we might want to choose those features which are sort of easiest for the person to change. And in fact, many of the papers that have proposed this kind of counterfactual explanation method have tended to adopt a heuristic which tries to find features that would be easiest to change. But the challenge here is that often the kind of feature values that have to change don't necessarily map onto discrete actions in the real world. So for example, along the lines of the example I gave earlier, let's say that a credit decision, an adverse credit decision, is explained by saying that you need to increase your income in order to obtain the loan in the future. But actually, there's sort of multiple real-world ways what you can go about increasing your income. So one way might be getting a new higher-paying job. Or another way might be that you sort of stay on your job but wait for a raise. Work hard in order to get a raise. The problem is that the model itself might actually be looking not just at your income, but actually might also be looking at length of employment. And in fact, this is a common feature in credit models. And it turns out that the actions I just described affect not only your income, but also simultaneously affect your length of employment. And so on the one hand, what this is showing is that sometimes features might not be independent, and explanations that choose to highlight one feature rather than another might not recognize that these features are in fact related to each other. But more than that, what this is showing is that in the real world, the actions available for people to take to change a particular feature might not narrowly line up with the specific feature that is being highlighted. And so this is actually a pretty tricky problem, in part because we often try to kind of give these discrete subset of features that are kind of most easy for people to change without thinking about this possibility. The second challenge we talk about in this paper is that, again, we might think that it would make most sense to tell people to change features which, in some sense, we think of as being the easiest change for them to make. But the way that we try to determine what would be easiest is often by just looking at the training data itself. So we say, it seems to be the case that if we normalize the features, these are the dimensions along which you, in your particular case, would have to make the smallest amount of movement in order to get to the other side of the decision boundary, for example. But the problem here is that we're sort of normalizing these features according to the distribution of those features in the training data, not according to actually in the real world what would make certain feature changes more or less costly or difficult. And I think what's particularly challenging here is that although we might have some intuitions for certain kinds of feature changes that would be more difficult than others, so for example, getting a new job might seem to be more challenging than getting a raise, perhaps. In practice, those costs of changes might vary considerably by person, right? So it's not just that these costs are sort of fixed and the same across all people that you might be subjecting to this decision. costs are going to be relative given people's individual circumstances, and it's going to be very difficult for any explanation to take that into account. And so while we might be sort of aiming to give explanations which seem easiest for a particular person, often what we're doing is sort of giving explanations that seem easiest in general for the population, even though we recognize probably, if we think about it, that circumstances and costs are going to vary dramatically by person. And this, again, is a very serious challenge. The third point we raise is that often the features that figure into a model might be relevant not just to the decision that is being explained to the particular person, but to many other decisions that person might care about. So for example, income might be an input to a credit model, but income is often something that's relevant to many other domains in your life. And so you might think that trying to explain to someone that, in this kind of hypothetical example, a credit model might say that actually you would be successful in your application had you earned less money, right? This is like unlikely to really exist. It's probably the case that most people constrain their model not to learn such a lesson. But if it were the case that a credit model expected you to earn less in order to be effective in your application, it might suggest that this is the explanation someone should receive. Earn $1,000 less, and then you would have been successful. The problem with this, of course, is that income, as I was mentioning, is relevant to many other goals people might have in their life. So it would often be irrational for a person to sort of narrowly choose to make less money in order to get credit, even though they know that income is valuable with respect to many other goals they have in their life. And so choosing what explanations to give really might be challenging when we don't have a full view into the way that these features actually are important to other goals and other decisions in people's lives. And the final point we raise has to do with monotonicity, as well as a number of other model properties, but I'll focus on monotonicity. So here, one of the challenges that you might say, like, okay, make more money, stay in your job a longer amount of time, and so on. And so you give some directionality for the change that someone should be making, and sometimes you even give a specific amount of change they should be making. And I think the kind of intuitive understanding of such an explanation will be that if I'm incrementally advancing the value of this feature toward the goal that you've given me, I expect that my chances of success are going to increase. But if it's not monotonic, it's very possible that actually as you kind of increase the value of this feature, maybe your chances get worse, right? And similarly, it's possible to imagine that people struggle to kind of meet the mark that you've given them, or maybe they even overshoot the mark because it's not possible to so precisely control the value of a certain feature. And if they overshoot the mark, maybe actually that's going to be worse for them than if they had, kind of undershot it or something like that. And so here, in the absence of these kind of monotonicity constraints, you might have people engaging what seems like the rational behavior that you've instructed them to take, but they end up being in a worse position than they would have been had they taken no action at all. And so in this paper, which I hope there's a link to, I think there is, yep, we try to explain how these are quite serious challenges. Or being asked to give explanations of these decisions will lack the necessary information to take these kind of factors into account, but that there's no easy fix for these, that there's no easy way to avoid them. And I'm happy, hopefully, to talk more about that in the Q&A. Thanks a lot.
All right. Okay, yeah, thanks, Sam. And yeah, to start off, let me just say that I'm going to repeat a few things that Raid said, but maybe with a different perspective. So firstly, why is trust becoming a top priority for companies? So it's because there's an increasing need to deal with more and more regulation. Companies are having to deal with increasing complexity of their machine learning deployments. They want to maintain their brand reputation, and in the current moment, they're also focusing on social justice. But when I talk about trust, what is trust? What does it take for someone or something to be trustworthy? So think about it for a moment, everyone. What does trust mean to you? So it turns out that in the organizational management literature, they've identified 4 attributes of being trustworthy. The first is being competent, so you do the thing that you're supposed to do well. The second is being reliable, so that competence sticks around in different conditions and so forth. The third attribute is being open, intimate, or communicative. And the fourth is being selfless, so working towards goals that go beyond yourself. And all four of these attributes are more or less the same, whether you're talking about trustworthy people or trustworthy machines. So for machine learning systems, what does that mean? So we want high accuracy that's going to contribute to the competence. We want fairness as well as robustness to distribution shifts and adversarial attacks. That leads to the reliability. We want interpretable and explainable machine learning systems, along with end-to-end transparency achieved by mechanisms such as fact sheets for the openness. And finally, we want machine learning to be developed hand in hand with its use for uplifting humanity. So one of IBM's early CEOs, Thomas J. Watson Sr., had this quote that the toughest thing about the power of trust is that it's very difficult to build and very easy to destroy. And I'm not going to talk about destroying trust here, but think about why is it difficult to build up the trust, especially for a machine learning system, right? So focusing on that third attribute of trustworthiness, which was the openness and communicativity. So what we need is actually a strong relationship between the human and the machine. And we're really dealing with a communication problem aimed at some sort of mutual understanding that we're trying to develop. So we want the machine to understand us and for us to understand the machine. Right? And explainability helps us to understand the machine. And as Raid was saying, I mean, there's different use cases, different personas, and everything has different needs. There's many ways to explain, and one size doesn't fit all. So repeating a couple of his examples, right? So if you're an affected user about whom decisions are being made, you're going to care about your own decision. And so local post hoc explanations tend to work well. And the sort of contrastive explanations that Solon talked about are relevant here, right? But regulators are in a different boat, right? So they need to understand the entire system and not leave opportunities for corner cases to wreak havoc. So they would actually prefer to work with directly interpretable global models so that everything is apparent in front of them. And this is the approach that our group at IBM Research actually took in winning the FICO Explainable Machine Learning Challenge, the directly interpretable approach, right? And more importantly, and most importantly, I would say it's the decision makers themselves who are being supported by the machine. So folks like doctors, loan officers, judges, and so forth, that have to understand how it is that the machine predictions came about so that they can assimilate those predictions with their own independent assessment to reach a final decision. And it's the need for all of these different ways of explaining, which is why our group has created the open source AI Explainability 360 toolkit as well. So coming back to this decision maker persona, right? So we should always remember that we're dealing with a communication problem. Okay, so the individual accuracy of the machine learning model is only one part of the overall accuracy of the decision making system, which involves both the machine and the human decision maker. Okay. So in some of our past work, we set up this explainability problem abstractly as a two-node distributed detection problem with the machine communicating to the human, right? So we mathematically proved using Chernoff information that more explanation yields better overall system accuracy. So this so-called accuracy explainability trade-off that some people refer to is actually false, right? So in some even more recent work, we've been looking at things again abstractly through this Chernoff information, and have been able to show that fairness can be actually improved by giving more explanation for members of unprivileged groups. Good. So this leads me to the final point that I want to make, which is that the community has started thinking in terms of different worlds or different spaces. So there's a construct space, which is a pristine world free of biases. And then we have the observed space in which we get the data, and it can have many different biases. And lastly, we have a prediction space, which is where machine learning model outputs live, right? And most of the work that kind of deals with the first two attributes of trust, including accuracy, fairness, and robustness, try to make sure that the mappings between these spaces are mitigated or defended against biases. But I would argue that there's a fourth space that I would add to the end, and that's a perceived space of the human decision maker. So the receiver of the model outputs is a person, and that person has inherent cognitive biases and limitations. And the information that they perceive or receive from the machine is colored by anchoring bias, confirmation bias, weak evidence bias, and so on. And we actually should be compensating for it as we work on explainable machine learning. So this is a sort of last mile communication problem, bridging the channel between the machine output and the human perception. And for intimacy, this third attribute of trustworthiness, we also have to go beyond looking at explanation as simply a math problem and really work on how to get machines to speak to people in our language, to speak to us. And the language of causality might help in this regard. And just to wrap up, let me just say, again, repeating some things that Raid mentioned, that having this broad-based perspective that touches on different ways of explaining different attributes of trust in different spaces needs to also be coupled with a tight loop of serving nonprofit and for-profit partners, conducting fundamental research, and creating open source toolkits, because I think that really is the best way to make progress towards machine learning systems that we as people can really work with.
Am I still muted? Was I still muted? Wow. So I was saying, Kush, that thank you for adding that. I think the idea of the perceived space is an interesting one, and going beyond explanations as math as well. And I think both of those are a perfect cue and tee up for the topic that Alyssa is going to be elaborating on, and that is a stakeholder-driven approach to explainability. All righty. Alyssa?
The opportunity to participate in the discussion today. It's a pleasure to share this virtual stage with you and other distinguished members of AI community. And let me preface saying that a lot of the things that I would like to say are very much dovetailing on what Raid and Kush already said. So we're very well aligned, even though we didn't really prepare. So my name is Alyssa Lapjinova. I'm the co-founder and CEO of a company currently in stealth that builds monitoring and debugging tools for enterprise AI applications. And today I'll talk about why it is crucial to define your stakeholders before you embark on designing and implementing explainability tools for enterprise AI applications. So a little bit about where I'm coming from. Throughout my career, I've been on a mission to build bridges between machine learning scientists, engineers, and executives. I did this in numerous capacities at Amazon and the Allen Institute for AI, now doing this at the startup. I spend essentially my days talking to engineers, scientists, and executives about deploying models to production, and I encounter challenges with model explainability deployments very often. And as you've heard from other panelists today, there are many nuances to model explainability endeavors. Let's focus on how to think about stakeholder personas when you're embarking on an explainability endeavor, and which personas can benefit from the techniques available to us today. So who are these stakeholders? Well, there are many types, and the ones that come up more often in an enterprise projects are builders, researchers, executives, regulators, domain experts, and end users. Other panelists have touched on some of these stakeholders already. A great example of a taxonomy of how to think about these different stakeholders is available in a paper called Explainable Machine Learning and Deployment by Umang Pat and his colleagues at Cambridge and Partnership on AI. Today, I will briefly focus on 3 stakeholder personas that come up very often in enterprise AI, and these are builders, regulators, and domain experts. These 3 groups are broadly compatible. They all deal with AI deployment in the wild. However, they present very different requirements for explanations. Moreover, the explainability technology that is available today offers very different degrees of benefits and limitations to each of these stakeholder requirements. So let's dive into each of these stakeholders very briefly. First, builders. Builders are the data scientists and engineers building AI applications in organizations. That's one way to define them. They look to explanations to aid them in validating, testing, debugging, and monitoring models and predictions. There are many open source and enterprise explainability tools built specifically for builder personas in mind, builder stakeholders in mind. The IBM 360, Fairness 360, and Explainability 360 was already mentioned. One limitation in the existing techniques for builder stakeholders that comes up very often is that explainability techniques typically have really high computational requirements and are infeasible to deploy at scale in real-time systems. So when you're building explainability tools for builders, one thing to keep in mind is that you need to design to avoid real-time requirements. However, that's just one limitation, and based on various industry surveys, we see that organizations are quite successful at deploying explainability tools for these stakeholders. So if you are considering an explainability initiative at your organization, the builder stakeholders are a good starting point. So the next group I mentioned of stakeholders are regulators. Regulators are either internal or external parties involved in audit and compliance activities for AI applications in highly regulated industries such as finance, insurance, and health. In the many cases, regulators look to explainability to understand whether a model presents bias towards a specific group. This requirement, however, poses a challenge because explainability techniques so far have proven unreliable in explaining models' fairness and bias. This limitation is really well demonstrated in a recent paper titled "You Shouldn't Trust Me," very fitting, by Boris Demanov and his Cambridge colleagues. So that's something to keep in mind when you're deploying explainability for regulators as stakeholders. Another challenge for this group of stakeholders is that techniques that rely on input perturbations are extremely vulnerable to adversarial attacks. This limitation has been exposed by Hima Lekkaraju and her colleagues in the paper called Fooling Lyman Chap. Hima is here today, and I'm excited to hear directly from her on this topic. So given these limitations, specifically for regulator stakeholders, an organization might decide that an explainability project for the stakeholders is not a feasible endeavor at the moment. There are, however, many excellent research initiatives to address both of these shortcomings, and I'm hopeful that we'll see solutions soon. So the final group I'll talk about briefly are domain experts. Domain experts are individuals who are tasked with auditing the model behavior and ensuring that predictions align with expert intuition. These stakeholders are most prevalent in human-in-the-loop AI applications, as Raid mentioned earlier. For domain experts, a core challenge with explainability techniques that I see is that most explainability techniques do not have causality and uncertainty underpinnings. This limitation makes it really hard to align explanations produced by explainability techniques with human intuition, because it's hard for humans to think without causality and uncertainty. So when building explanations for domain experts, it's important to educate them about the lack of causality. And as far as uncertainty goes, there are some emerging techniques such as CLUE that incorporate uncertainty. You can check out a paper called Getting a Clue, very fitting, by Javier Antoran for more details on that technique. And I'm hopeful that we'll see more explainability techniques that are intuitive and have causality and uncertainty underpinnings. So in conclusion, we live in an age of tremendous progress in AI. We have incredible researchers working on moving the state of the art. And explainability tools and techniques are being developed, new ones every month. However, I think there's a disconnect between what existing techniques are capable of and what the practitioners require. So in order for the state of the art to move in the right direction, I believe organizations which are implementing explainability techniques internally need to define stakeholders, carefully outline requirements, and identify limitations with existing explainability techniques. These requirements and limitations then can be shared with the research community. And by facilitating such community engagements, we can push the state of the art forward and better address the problems that are faced by practitioners today. And I'm excited to talk more about this in the Q&A. Thank you.
Awesome. Thanks so much, Alyssa. I think that was a great talk, and also a great summary, I think, of some of what we've talked about thus far. And as well, a great introduction to Hima's talk, who is up next.
Yeah, thank you, Sam. Hi, everyone. Thank you so much for having me here. I'm super excited to be part of this panel with other amazing guests here. And I'm so glad that I'm going after Alicia, because she has given, as Sam pointed out, a very nice introduction to some of the problems that I'll be talking about today. So over the past year or so, me and my group have been spending a lot of time thinking about understanding the vulnerabilities of post hoc explanation techniques and how these vulnerabilities can be exploited by adversarial entities to generate misleading explanations, and how to mitigate these vulnerabilities. Alongside these, we have also thinking a lot about what are the different ways in which domain experts in different domains might actually interpret explanations? And does that match a designer's understanding of how an explanation would be interpreted? So I'll just give a quick summary of some of the recent work that we did in this space. And I think the links that I've already provided to Sam should hopefully be up, and you can know more about these topics through those links and documents. Okay, so let me start with one of the pieces that Alicia pointed out, which is a lot of the explanations that we have today are not necessarily causal, and they're counterfactual. That really affects how domain experts think about explanations, and there is a risk that the explanations might mislead them to trust a model that they should have not trusted to begin with, right? Is this the case, or are domain experts really understanding the models or the explanations the way they're supposed to be understood? We were very curious about this question, and we did like a user study with law school students, about like 50 to 60 of them. What we did at a high level was we constructed a classifier, which is a rule-based classifier, which uses race and gender as predominant attributes when making decisions as to if somebody should be released on bail or not, right? So clearly, we explicitly tried to design a biased classifier. And then what we did was we constructed an explanation, which is also the same kind of rule-based model, which means the functional forms are the same between the explanation and the actual biased classifier. And this rule-based explanation, while it mimics the predictions of the biased classifier, it basically visibly removes race and gender as the features in the explanation. So potentially we had replaced those race and gender features with their correlates, which means the explanation is doing exactly the same thing as what the model is doing in terms of predictions. It's just that visibly the explanation does not show features like race and gender, thus making it look innocuous. Then what we did was we recruited these 50 to 60 law school students, and we basically randomly assigned each candidate or each user either to this actual true rule-based classifier, which has race and gender in it. And on the other side, we assigned some users to the explanation, which looks innocuous, but basically does the same thing as the classifier, right? And when we ask these people a question which reads like, here is an explanation provided by state-of-the-art machine learning. Looking at this explanation, would you trust the underlying model enough to deploy it? when we asked this question to them, of course, people who saw the true bias classifier with race and gender as predominant attributes said, this is not trustworthy, we don't want to deploy it anywhere. Whereas people who looked at the explanation where race and gender were removed, and in fact, we had also added a couple of other attributes like prior arrests and so on, which were often things that domain experts thought should appear in these kinds of models when making decisions. In that case, the overwhelming majority said, oh, this looks innocuous, this seemed to have a high accuracy, this is mimicking the underlying model well, so yeah, we can trust it. Right? So the simple kind of visual distortion has already confused people into trusting and potentially agreeing to deploy a model that should not have been deployed in the first place. And the issue is, as Alicia pointed out, that explanations are not causal. At least most of the explanations generated by techniques today are not causal, and that needs to be communicated appropriately to the end users, domain experts, because for them, the notion of explanation seems to be strongly coupled with thinking causally. So that is one piece. And then the second piece that I'm super excited about, which Alicia again gave a quick peek into, which is we also thought a lot about designing adversarial attacks for existing post hoc explanation techniques. For example, I'm sure a lot of you are already familiar with techniques like LIME and SHAP. So one of our works basically deals with how can an adversary attack methods like LIME and SHAP in order to generate explanations which look innocuous, but actually they kind of are misleading. So the explanation is kind of designed, the attack is designed to fool the explanation method to generate a misleading explanation. And at a very high level, the intuition for that, for this work is also comes from some of the vulnerabilities of these methods. The main one being methods like LIME and SHAP rely on what is called as perturbations, which means methods like LIME and SHAP typically try to explain individual predictions of a classifier. So what these methods do is you pick a point that you're trying to explain, perturb the point, generate a bunch of instances, and then build a linear model, for example, on top of this, which is interpretable enough so that you can read the coefficients of the features and understand which feature is important and by how much and so on. So that's the rough method that they use. What we found during some of the experimentation was that these perturbations that are being generated by these methods are actually out of sample. They don't correspond to the distribution of the actual data instances, which means an adversary can potentially exploit this and basically design a simple wrapper which does the following to fool this explanation method. What could the adversary do? The adversary could basically say that if a data point is likely to have come from the distribution of the data, then do something unfair with it. Like, for example, maybe use race or gender or other sensitive attribute in determining its label, right, or its prediction. On the other hand, if the data point is a perturbation, which is kind of out of sample, then what you do is you basically try to keep it very fair, or use some very innocuous attribute to give its prediction. By doing this, what happens is you're creating a classifier that is very fair on the perturbed points, but very unfair on the actual instances. Since LIME and SHAP rely a lot on perturbations to generate explanations, this kind of drowns out the fact that the model is being unfair towards the actual data instances, drowns out completely. And what you see in the explanation is the innocuous variables that are being used to make predictions on the perturbations or the perturbed data points. So that's another very simple attack which breaks these kinds of methods. And lastly, we have also been thinking a lot about solutions to these problems. And recently we have another work at ICML where we basically thought about, or rather, proposed to bring ideas from adversarially robust classification to explanation methods, and use those ideas and, of course, adversarial training and so on to come up with explanations which are generally robust to shifts in the data and are also more stable. So these are two problems, as Kush mentioned, for the current explanation techniques. To alleviate those, we also proposed using adversarially robust classification techniques. So with that, I think I would like to stop there and give it back to Sam.
All righty. Thanks so much, Hema. All right. So with that, we are ready to transition to the discussion segment of our broadcast today. Please take this opportunity to get your questions into the chat. You're probably watching this on YouTube. If you would take a moment to hit the like and subscribe button down below, we would certainly appreciate that. And to my fellow panelists, this is an open discussion. You're welcome to ask questions as well of your fellow panelists. I will be relaying questions in from our audience. And to get things started, I wanted to maybe just kind of recap a little bit. I think the key takeaway for me from the kind of the sum total of all of your talks was that, you know, while it can be tempting to kind of take an explainability algorithm off the shelf and think we're just going to sprinkle it on our algorithm, there's a lot of work and thinking that needs to go into making this process work in the real world. We need to be thinking about the use cases, which Raid provided a taxonomy for. We need to be thinking about who the algorithms are for, and Alyssa's personas were very interesting there. Several of you touched on the forms of these explanations, whether causal or otherwise. The receiver of the explanations came up a couple of times, the personas again, as well as this idea of the perception, so getting in the head of the person who's seeing the explanations. And of course, the issues around trust and vulnerability. Trust came up several times. And of course, Hema focused on that. One question that comes up quite a bit in this conversation around explainability is the idea of explainability versus interpretability. So kind of an inherent interpretability of the models versus explainability versus being able to explain them. And I'd love for you all to speak to that issue. There's a bunch of questions there. Questions like, should we be, when and where should we be using models that aren't explainable or aren't interpretable inherently? But I imagine this is something that you all have takes on. So I'll just go around the horn with this one, starting with you, Hema.
Oh, great. Thanks, Sam. So I remember having this discussion with you. It's like a deja vu, but yeah. So yes, I think, both interpretability and explainability today clearly have a place in our literature, because we see, multiple research articles and papers being published on both these topics. And I think my take on it, and I would love to hear what others are thinking about this, is, since we are already, I think this talk itself kind of exposed a bunch of, vulnerabilities or things that we need to be mindful of when thinking about typically post hoc explanations, right? So because, we are not exactly sure that current algorithms are, or rather we are sure that most of the current algorithms are generating more correlational explanations and not causal ones, whereas people are interpreting an explanation to be causal and not correlational. So there are a bunch of different kinds of gaps there. So if given a chance, and if your domain is permitting you to come up with an interpretable model from scratch, and you have the infrastructure to do so, you have the data to do so, your model is accurate as well as interpretable, that is probably the best and most safest route to go. On the other hand, that is also probably somewhat idealistic given the various, like different aspects in the setting. Like, for example, maybe you don't have enough data to train a model that is accurate, or you're seeing that there is a trade-off between accuracy and interpretability, and you're coming up with a complex model because you can't afford to not lose the accuracy, right? So in some cases, what you have is like probably a company or another organization has handed to you this black box that for whatever reason a doctor in a hospital is being asked to use because the organization has made that decision, for instance. And in this case also, you'll not have access to the internals of the black box, and most likely the black boxes might also not be interpretable on its own. Right? So in all these cases where you can't afford to build or train your interpretable models from scratch, then the only option that is left with us is to fall back to post hoc explanations.
Any reactions to that? Unmute if you've got something to tag on.
I'd like to +1 this a few times, and one thing that I may add is when working with organizations and practitioners that are, kind of asking themselves the same question very frequently, what I feel is missing is exactly what image ed, but made written up in a very accessible manner, again, as some kind of guide of how to think about these trade-offs. I feel like a lot of people start with this question and go on kind of this endeavor, reinventing the wheel and looking for the solution. And this happens over and over in every organization. I think it would be beneficial to have a resource for that.
I mean, I think,
right.
So one question is, we talk about these hypothetical trade-offs, yet we've never really, there's no good study that actually looks at a real problem, real data, looks at 20 problems and says, here is the actual trade-off. Right? Every paper that I've seen on sparse models is using some dummy data set on some fake problem and some fake metric. So I think before we sort of even talk about a trade-off, we kind of need to figure out whether there is one. And if there is one, then we should figure out how to balance it and talk about it. Right now, we're sort of assuming that there exists some sort of a trade-off. And then the other sort of misconception that I run into a lot is at least I don't trust my ability to interpret models. Even if I see a regularized regression with 6 features, I have no idea how to play the mental gymnastics of, well, this one is controlling for that, and this one is controlling for that. Like, I have no idea. Even if I see a decision tree with, more than 3 deep with more than 6, 7, 8 variables, it's very hard to really understand what's going on. And then how it generalizes over time. Like, you can do it for one time period, but so I think it's kind of hard. I would claim no actual practical model using even the basic machine learning is actually interpretable. So you need tools to give people to help them understand what it's going to do, when is it going to do it, what are the, to this is your point of confidence around it, uncertainty, all sorts of things. And it's a toolkit, right? It's not a thing that you set. Feature importance is not an explanation. It's feature importances. That's not, so I think we kind of need a little bit of sort of, let's step back and think about what are we trying to do. We've got a lot of research. Like, people have spent years doing this. Maybe we need to kind of think about, okay, this problem is solved. Let's stop working on this. Let's go to this problem. So there's a kind of thing. I think we sort of need to think about what do we need to achieve in these problems, and then kind of focus the research on filling those gaps.
Right.
I was just going to go
ahead.
Sorry, Sam. I was going to say that it was funny because what Raid said is exactly what happened when a few colleagues and I a couple years ago were trying to look for papers that sort of showed this trade-off empirically, because it's sort of taken for granted. And I think there is some basis in reality, right? Like, practitioners are certainly encountering this trade-off, but the idea that there's like a formal proof that shows this is not the case, and there isn't any systematic empirical study that shows it, which was very surprising. And I think one of the challenges is like, yeah, having real cases to do this on. But another point that I think Raid made that I just want to emphasize is like there also isn't a clear definition of interpretability. So we have like, again, these heuristics that say like, okay, sparse models, simplicity, some measure of simplicity, maybe decision trees, these things like strike us as being interpretable. But again, like there isn't some formal way to actually define this. And often we use some measure of sparsity or simplicity, but that's just a choice. We could do it some other way. And it was very surprising to kind of discover that even interpretability, which has a much longer history actually than explainability, doesn't really have that as well. So I think that really does suggest that like the way forward here is to think concretely about real world cases where people have very specific domain specific concerns, and then try to do some of this empirical evaluation, because to answer this in the abstract just basically seems impossible.
Yeah, speaking of the concerns of stakeholders, there's a question from the audience: do stakeholders have reasonable explanations when it comes to explainability? Alyssa, you spoke a bit about kind of the stakeholder perspective and your experience building these systems for folks. What's your take on that?
Do stakeholders have an explanation for
reasonable expectations when it comes to explainability?
Expectations. I would say confidently no. Partly because what we just heard from both Solon and Raid, that the definitions aren't even clear. Even if you're talking about a very simple model, linear model, if it takes in thousands of features, even hundreds of features, what does an explanation mean there? How can you kind of comprehend with your human mind what's happening and what's important in the prediction of that model? So I think the expectations are not very clear, and it's in part the responsibility of us as a community to set these expectations. And I think media kind of makes it slightly difficult, because whenever there's a new explainability technique that's super exciting, we see articles saying like, whoa, everything is explainable, hooray, let's go. And that makes the whole expectation setting process quite a bit of a challenge. I'd love to hear how others in the panel think of how we can go about setting the right expectations.
Kush, any takes on that? I think you're frozen. Oh. Anyone else on the panel have a take on that one?
I mean, one thing to keep, I think it's on the trust use case, right? A trivial way to get trust is to tell the user what they believe is already true. Yeah. That, and you pass the trust test. But that's clearly not what we want, right? Because and I mean, then you're a politician, basically, if that's, and we can do that. I mean, the other, so that coupled with what are we comparing these systems against, right? What is our baseline in terms of explainability? Is it the human decision maker that we're comparing against? Of human makes a decision, we ask them, why did you make the decision? They give an explanation, and then the computer makes a recommendation, and we compare them. And again, it's unclear whether in most machine learning problems, a human existing baseline is a good baseline. In interpretability, I'm not sure or explainability, if that's the right baseline. Right? I think that's the other piece is, another one we do with baselines and evaluation is we ask a person, did you like the explanation? Well, I don't care if you like the explanation. Did you find it, did you make a better decision using it? In some use cases, right? In the recourse, I don't care if you made a better decision. I just want to know that if, in that case, the evaluation is, if you modify this variable, tomorrow the decision will change, right? So I think even the evaluation piece in terms of each of these, they're all different metrics that we have to use to kind of see how well something works. And in some cases, humans are, in most prediction problems, and this is something, I think in the podcast we had, whatever, a year ago or so, we talked about it. If we're dealing with kind of the classification problems, humans are good at some of those, image classification and text and on all those things. And so an explanation can be evaluated by a human as, yeah, I kind of agree with you. In prediction, humans are pretty bad. And that's the reason we're using ML, is because humans are pretty bad. We're not using it to scale the computer. We're using scale the human. we're using it to improve over the human, in which case the explanation is, human may not be able to judge the explanation as being good or bad. It's the decision they make that we judge the system by. Is this human computer, does the overall system do better than just the computer or just the human? And I think that's it's a nuanced difference that you can't churn through that overnight on your computer and run experiments and produce results, right? It's a much more complicated process. And I think by defining it really well, the new people who are getting into this area, the new researchers, I think that's where we need to kind of help guide and like, okay, if you're going to focus in this area, then it's going to require, it's not just a data set and run models and generate results and explanations. You're going to have to work with these people.
All right, we had a couple of questions directed at you, Solon, looking for additional examples. One was use cases in which automatically generated counterfactual explanations were acceptable under the law. The person thought you mentioned that and wanted some examples. And the other was an example of a causal-ish explanation without an explicit causal model. I think also referring to something you mentioned.
Sure. So in this paper, actually, that I drew on to present today, we talk about two different areas of law where it seems like counterfactual explanations might satisfy the requirements. So recently, there's been a lot of interest in the European General Data Protection Regulations apparent right to an explanation. And there's a lot of debate about whether that right exists and what form it would take. But generally speaking, there is kind of formal guidance by regulators that gives the sense that a counterfactual explanation would likely satisfy that requirement. And so here, the kind of law applies quite broadly. So if there's an automated decision that kind of reaches some threshold of significance, then you are entitled to such an explanation. It's not yet clear where those methods are being used and what regulators will really think about them. It's still early days, but that's the general thinking. But actually, in the US, as I mentioned, there are credit laws that are now over 40 years old that have so-called adverse action notice requirements. I sometimes, when presenting, ask, has anyone ever received one of these? And I learned the hard way that no one wants to admit to being rejected when applying for a loan. But if you are, what you do get is a kind of statement of reasons. And they'll often say things like I mentioned, insufficient income, or maybe there's some mark against you in your credit file, like bankruptcy in the past or something like that. And there's some thinking that perhaps counterfactual explanations can be used to generate these so-called adverse action notices, right? Identify the specific reasons why you've been rejected. The one thing I'll note very quickly is that it's funny because as I mentioned, this law, this requirement is quite old and predates the use of machine learning in many of these industries. And the method that the regulator has proposed for generating these reasons is completely different, actually, than counterfactuals. What they actually tell people they could do is actually find those features that for the particular person, that value of that feature is furthest from what the average value of that feature takes in the entire population or in the population that would otherwise receive credit, which is almost the flip of what you would have in counterfactual explanations, where it's often trying to point out the things where you're kind of nearest the easiest change you can make. And what this suggests is that it's almost serving a different purpose. And this maybe builds on what Raid was just mentioning, right? Like, it's almost trying to get people to accept their fate, right? Like, you are so far away from the value this feature needed to take that, like, that's it, that's why we've ruled you out. Which is a completely different way of thinking about the purpose of explanations than the way at least counterfactual explanations more recently have formulated it, which is often like, here's the simplest and easiest thing for you to do. And so there's some interesting questions about whether these existing laws can, in fact, be satisfied by this method, given that actually the proposed method from many years ago is quite different.
Awesome. A couple of questions for you, Hema. The first is there some way to evaluate the synthetic neighborhood generated during post hoc explanations?
Yeah, that's a very good question. So yes, like not, there is no paper or anything like that that I can immediately point to. But yes, if you're somehow able to approximate, like for example, let's say if your data has infinite samples and you know the complete distribution and the associated likelihood of a point being generated from that distribution, then clearly you'll know an answer for whether a perturbation is valid or not, right? Whether it comes from that data distribution or not. But that is often not the case. So we'll have to like work with finite samples and come up with approximations to figuring out the likelihood that a point comes from the distribution or not, for which there are ways to approximate it. While there is no, like, I can't point you to one paper, there are ways to do it this way.
Great. And then the other question is, in addition to what you said about the auto distribution points, are perturbation-based methods also vulnerable to less meaningful explanations for certain regions of the data set, such as protected classes?
That's a good question. I don't have an answer off the top of my head, but I guess perturbation-based methods do have some of these instability problems and so on as well, but that could potentially cause issues for like generically, kind of a very subgroups with very small representation in the data. So potentially minorities could be associated with such subgroups which are much kind of less represented in the data. So there is that chance, but I don't have a very strong answer to that question yet. But that's a great question. Check that, yeah.
Let's see if we can get a quick question in for Kush while his internet is somewhat stable. You mentioned explainability increasing fairness. Can you elaborate on that?
Mm-hmm.
Is this a possible solution to the impossibility results in observation-based fairness?
Yeah, so apologies again. I think it's remnants from last week's tropical storm that are still affecting some infrastructure here. But yeah, so related to that point, so what we were able to show was, again, talking more in an abstract sense, not necessarily on specific algorithms, but we have the general idea that the more separation that you have among the predicted labels, the easier it is to perform the prediction task. And when that's different across groups, let's say there's a privileged and an unprivileged group, that separation is different across those groups. And what we were able to show was that, in fact, adding extra explanations and also actually adding extra features for the unprivileged groups increases their separation and allows you to actually have better prediction quality for the unprivileged group. So that's kind of what we had been talking about in the work that we did. And I think this points to, a lot of different issues. What are we, hoping to gain? So first of all, we have to make sure that we're talking about a setting where there's a human who's the final arbiter of the decision, because if it's a machine acting autonomously, this isn't really an issue that should be coming up. But when a machine is taking somewhat of a decision, maybe it's a soft decision, and passing it on to a human, that's where there's more of a need for this sort of explanation, and that's where these sort of things help.
Right. And then another question for you, Kush. Can you elaborate a bit more on the link between explanations in those 4 spaces that you identified? And in particular, are you suggesting that the explanations should contain elements or components from each of those spaces?
Yeah, so just to repeat, so we had the construct space, we had the observed space, we had the prediction space, and then a perceptual or perceived space. So there's not really much to be done in terms of explainability, in my opinion, going from the construct space to the observed space. Those are kind of data sort of questions, which there's, many other ways to look at. But once you have your observed space, so that's the data set that you have to work with, then moving into the prediction and the perceived space, again, where the perceived space is where the human is going to be looking at things and making their final decision. So the human gets some observation directly from the observed space, and then they get the output from the machine learning model, which is in the prediction space. So there's roles for explanation in both of those sort of arrows, going from the observed space to the perceived space, and from the prediction space to the perceived space. And I think, I mean, there's different ways of doing things, as I said before. So model explanations are clearly useful for going from the prediction space to the perceived space. But when you're going from the observed space to the perceived space, that's where data explanations are just as useful. So I think, and then, I mean, what are specific methods for doing this? As Hima was touching on the very first question, so I think, I mean, there's different ways of explaining that are more or less relevant on what you have the ability to touch. So not every situation allows the user to actually touch the training data or touch the model or other parts of the life cycle. So I think it's, I mean, this sort of holistic question, what can we change, what can we affect? And having the big picture lets us actually make more reasoned and sensible judgments on that.
Great. So you've all, to some degree, touched on how the vagaries around how we measure performance of these explanations, whether we're asking humans to rate them or otherwise. Interesting question here suggests what can we do to kind of push this forward? Like, is there an ImageNet moment for explainability where we really nail the benchmark, and if so, what might that be? Any takers on that? And for that matter, what how close are we? Is there what are the metrics that folks are using, and what are their standard benchmarks? What are they lacking? That kind of thing.
So I can, start, and I think the best way to start is actually to point to a paper from 2017 by Bean Kim and Fenali Doshi-Velez, because they really, go through different levels of how to judge interpretability and explainability, starting with, just assuming that something simple is interpretable, going up to some proxy measures that you compute something, and then finally having the human in the loop to actually give you user studies and judgments. And as you go up this ladder, there's more and more cost involved. It's much harder to do. But I think at the end of the day, ultimately, it is the final human judgment, and you have to have the right population to be doing this judgment as well. So if you want a medical diagnosis system and you look at mechanical Turkers as your population, that also isn't going to work, right? So really, the ideal situation is to get to the user population that are the true consumers in the context that they're going to be making those decisions. But again, you have to step back as needed to make progress.
Just continuing on that, I'd like to add a couple of points. I think the 3 levels that the paper mentions and what Kush is talking about is, one is you just have quantitative metrics, like let's say, number of rules or number of, the features with non-zero weights in a linear model and so on. So these are metrics that are like super easily computable. And then the next level is proxy tasks. Like let's say if I'm building an application for like a judicial system, right? So it is hard for the system to be deployed in the setting and get tested and so on. So you kind of come up with some proxy tasks. Like if I, probably use a Turker, like would the Turker be able to simulate a prediction using the explanation we have or not? So that's the second level, which is proxy tasks for the actual task. And then the third level, which is most difficult to execute, is in deployment and actually seeing how interpretability is improving the efficiency and accuracy of the decisions. But I can see, like, while the third level is the most ideal, I can see that getting there can be extremely difficult, like, for example, especially through academic labs and so on, and, reaching, like, for example, courts in the US, or like, getting a hospital to deploy your system and then study what its effects are. These are all kind of much more challenging things to achieve in practice. So people typically resort to either the proxy evaluations, or they go to this like quantifiable metrics like the complexity or the size of a model and things like that. So, yeah.
Great. Solon, you had a bit more to add on the topic of interpretability. Chime in on that.
Yeah, no, I think I share Hima's view on this. It's that I think ideally these would all be kind of context-specific evaluations, and what Kush was describing, I think, is obviously the kind of perhaps like gold standard. The challenge is like being able to accomplish that in practice. I mean, I think the harsh reality here is that like there is no perfect answer, right? And I think as a field of study, this is maybe unlike other things where you can just max out accuracy. We actually have to think very carefully about the domain we're working on. And that's just the nature of the problem here. So there's never going, yeah, I think what I was saying is like there's never going to be like a universal definition of interpretable, in the same way that there's never going to be like a universally good explanation. These are only things that can be defined by looking at the context of use.
It's about time for us to wind down, Solon. I will take that as your kind of parting thoughts on the comments, and I'll go around the horn and get everyone's kind of final word and thoughts on the discussion today. Raid?
Let's see. So two final thoughts. One is, I think, like any other component of the overall system, interpretability is a piece that we have to evaluate and think of in context of how does it help us improve the overall goal of the system we're building. It's not a thing by itself, just like the model is not the thing by itself, and just like the data is not the thing by itself. So I think that's one thing, is getting stuck in interpretability without the overall context doesn't lead to productive outcomes. The second thing I think, which worries me a lot about this field right now, is I don't want this to become an elitist field where only rich universities that have access to people and problems and data, or large companies that have these systems can do this research. Because we're all saying it needs to be situated in context with people, with problems, in high-stakes situations. Well, that's going to be, then you become economists who have privileged access to data, and it's a totally unfair field, and we don't want to get there in many ways, right? I'm going to get spam hate mail now from economists. So I think we have to figure out of the field, how do we, to your point, Sam, of how do we create some of these proxy tasks that are correlated with good performance on the real task, so that people are not completely wasting their time. And then once they pass certain tests, how do we give them a collaborative infrastructure where they can test out some of these things on low-risk real problems and low-risk real users? I don't have an answer, but I'm hoping people listening to it and colleagues here on the panel have ideas on how to achieve that.
Great. Hima?
Okay, let's see. I think my parting thought would be that in terms of the research and the challenging problems that are still out there to solve, explainability is like, I think, one of the fields that's right up there at this point. So that's like a call for all the young researchers out there, and anyone who is kind of thinking about, if I should venture into it or not. I think I just want to encourage them to also be a part of it, firstly. And second thing is, just to practitioners and folks who are also researchers and so on, I have few kind of nuggets of wisdom probably that I got to learn through trial and error in my own research, and seeing me fail in certain experiments and so on. One is, for practitioners, I would kind of encourage them to engage more actively with the researchers, and vice versa, when designing tools that are, so to say, interpretable or explainable, and not to take anything on the face value. This is also for the practitioners both as well as the researchers. If a method claims to be explainable, don't just accept that it is going to do what it is telling that it would do. Be somewhat skeptic and have your own checks in place, checks and balances in place. But that said, I think we do have some challenges, I think, through all the questions that came out, that there is still a long way to go in terms of coming up with the ideal view of like what interpretability or explainability could be. But I think we are slowly getting there, hopefully through trial and error.
Great. Kush?
Yeah, so I think I'll kind of echo, many of the things that Solon, right, and Hema have already said. And kind of say, I think we're at a stage where, we have a good set of methods that fit a lot of the taxonomic sort of...
I thought we were good with Kush to close out.
subcategories. Did I break up?
You did.
Oh, am I on?
We can now.
Can you hear me now? Yes. Okay, great. So very quickly, so that I don't drop again. So we need that next level up and have some sort of meta algorithms that really help us as people understand the context better, and are trying to, figure out and help us figure out, what is the best approach to. That's kind of my parting thing, and I won't go into more detail for so that I don't drop off again.
Got it. Meta algorithms to help us figure out what is the best approach. Alyssa?
I think this panel is ending at a beautiful moment. The amazing researchers that are here in the room are all looking for ways to engage more with practitioners to design experiments that actually touch on real world deployments, to figure out how to get to that third stage of evaluation of actually seeing how explanations are being used in a deployment. And from what I see from my side, talking with practitioners every day, they want the same thing. So I think the problem that we got to solve is, how do we all work together? And I will volunteer some of my time and say that I talk to a lot of organizations literally every day. That's my job. And if I'd love to help facilitate some of these discussions, given that we have good requirements for what type of organizations can participate in moving this research forward. And both the panelists and the listeners, please feel free to reach out to me. I promise I will actually follow up, and would love to connect you to practitioners and organizations to facilitate moving the state of the art forward.
Awesome. Well, thank you all for participating in this panel. A really great discussion. Thank you to our audience as well for your amazing questions. And thanks once again to IBM for sponsoring this discussion. Be sure to subscribe, visit our newsletter page to sign up for future notifications. And this video will be immediately available on YouTube. So feel free to review it for any references you missed, or share it with your friends. Thanks so much, everyone.
Thank you. Thanks, everyone.
Thanks a lot.
Thank you, Sam. Thank you, everyone.
Bye.
Bye.